In this set of notes, we're going to continue looking at different ways that we can find derivatives. So just as a reminder, up to this point, we've seen how to take derivatives of power functions, when we're adding and subtracting functions, when we have a function multiplied by a constant, when we have a product of functions, when we have a quotient of functions, and now we're going to look at how to take a derivative when we have a composition of functions. And so when we have a composition of functions, we can apply what is called the chain rule. And so the chain rule states the following. It says if g is differentiable at x and f is differentiable at y is equal to g of x, then the composite function f of g at x is equal to f evaluated at g of x. And it's going to be differentiable, and the derivative is given by this right here. And so we're going to look at several examples where we're going to take derivatives of composite functions, and as we take these derivatives, we'll also talk about why each of the functions we're looking at can be considered to be a composite function. And so first of all, we're asked to find the derivative of g of x is equal to x to the fifth plus 1 squared. And so we actually saw an example like this one already, and we saw that we could either consider this to be two functions multiplied by one another and use the product rule, or we could consider this to be a composite function. So how do we consider this to be a composite function? Well, first of all, notice that the inner function is x to the fifth plus 1. And then the outer function we could use h to denote this is h of u equals u squared. So the reason I'm using u here is I don't want to use h of x because we've already used an x previously. And so what the composition function is saying is it's saying we're taking this function right here, the x squared plus 1, and we're applying the function u squared to it. So in other words, we're going to square x squared plus 1. And so for this reason, we can write that g of x is equal to a composition of two functions, the x to the fifth plus 1 and the h of u equals u squared. So in order to write this as a composition, I'm going to say that f of x is equal to x to the fifth plus 1, and then we can write this as g of x is equal to h of f evaluated at x. And further, we could have also written this as h evaluated at f of x. So in other words, if I were to write out h of u is equal to u squared, well, if I were to evaluate this at h instead of at u, but rather at f of x, so h evaluated at x squared plus 1 is equal to, well, h is u squared, so this is going to be x to the fifth plus 1. So notice there's multiple ways notationally that we can write out composition functions, but the important piece here is this idea that we have a function that we're going to put inside of another function. And so that's when we have a composition function. So let's now look at taking the derivative. So notice up here, to take the derivative, I'm going to need both the derivative of the inner and the outer function. So first of all, I'm going to find the derivative of the inner function. So f prime of x, well, here is my f of x up here at the top, is just going to be 5 times x to the fourth by the power rule. And then I also need to take the derivative of h of u. And and h prime u is going to be equal to 2u. So what we want to do next is we want to evaluate h prime of u at u is equal to f of x. And so that's going to give me this first piece of the chain rule. And again, remember that the use of f and g, that's just going to change in context of the problem. So that's why down here I don't have the exact same letters as what is in the rule, because it's just going to depend on how we define our functions. And so this yields h prime evaluated f of x is going to be equal to 2 times f of x. And again, that's because h prime of u is equal to 2u. So h prime evaluated f of x is going to be 2 times f of x, which is 2 times x to the 5th plus 1. And then thus, to find the derivative that we actually want, which is the derivative of g of x, we know that by the chain rule, that the derivative of g of x is equal to, coming up here, since it is that composite, it's going to be equal to the derivative of h of f evaluated at x, which again by the chain rule is equal to h prime evaluated at f of x times the derivative of f of x. Well, we already found both of these pieces, and so we have 2 times x to the 5th plus 1 times the derivative of f of x, which is 5 times x to the 4th. And then as always, we do want to simplify that out. So that is equal to 10 times x to the 9th plus 10 times x to the 4th. And if you go back and you look at page 2 of our previous note set, where we use the product rule to find this derivative, you'll see that we got the exact same solution. And so having all of these different tools to find derivatives is very important, but it's also important to remember that when we're finding derivatives, there isn't just necessarily one rule that we have to apply. There are often multiple avenues to finding different derivatives through application of all of the different rules. So it's not just a one, there's always just one rule that we're going to use. And so that's why it's so important to practice all of these different rules so that in different situations we can see, hey, I could apply this one or this one, and sometimes I could apply either of them and get to the same derivative. So let's look at another example here. So here we have x to the 5th plus 1, and we have the square root of it. So starting out here, notice if we set g of x to be equal to x to the 5th plus 1, I can think of that as kind of being the inner function, and then the function that I'm going to apply to that function is going to be the square root function. And here we're going to say that h of u is equal to the square root of u. So then we could write this as a composite function, and we would have that f of x is equal to h of g evaluated at x. So what I'm going to need to do is take both the derivative of g of x and h of u. So we find that the derivative of g of x by application of the power rule is 5x to the 4th. And similarly, we can find the derivative of h by applying the power rule, because notice this is equal to u to the 1/2 is equal to 1/2 u to the negative 1/2. So just like before, the first thing we need to do is we need to evaluate h prime of u at g of x. So in other words, we need h prime evaluated at g of x. And so notice that's going to be equal to 1/2 times g of x to the negative 1/2. Or we could write this as 1/2 times the square root of u, which is going to be equal to 1/2 times the square root of x to the 5th plus 1. So therefore, similar to the previous example, by the chain rule, we know that the derivative of f of x, which is what we're really interested in, is equal to the derivative of h of x evaluated at g of x times the derivative of g of x. And so this is going to be equal to 1/2 times the square root of 5 to the x plus 1 times 5x to the 4th, which is equal to 5x to the 4th divided by 2 times the square root of x to the 5th plus 1. And so one way not to get lost in the notation in words, what we're doing when we take the chain rule is we're recognizing that f is again a composition function. And you can think of it having the inner function and the outer function. And so the inner function is the function that you're placing into the other function. And so what we're going to do is we take the derivative of that outer function, keeping the inner function the same, and then just multiply that by the inner function's derivative. Right here we have another example. And so again, we can see this is a composition function where the inner function is x plus 2 divided by x minus 3, and the outer function is going to be u to the power of 3. So here, we're going to define this to be if g of x is equal to x plus 2 divided by x minus 3, and h of u is equal to u cubed, then just like before, notice that f of x is a composite function. It's equal to h of g evaluated at x. So by the quotient rule, and notice I need the quotient rule here because g is a quotient of two functions. So here I'm going to let u be equal to, oh, and actually I don't want to use u here because we're already using u up top. So instead, let's let w be equal to x plus 2 and v be equal to x minus 3. So notice that w prime is going to be equal to 1 and v prime is going to be equal to 1. So by the quotient rule, we know that g prime of x is going to be equal to the derivative of w times v minus v times the derivative of w. Oh, sorry, I said that backwards. V prime times w, all divided by v squared. That's going to be equal to 1 times x minus 3 minus 1 times x plus 2, all divided by v squared. So simplifying this, we're going to have x minus 3 minus x plus 2 all over, and instead of v squared here, I should have wrote x minus 3 squared, x minus 3 squared, which is equal to minus 5 over x minus 3 squared. And so next, we could find the derivative of h of u. And so by the power rule, we know that the derivative of h of u is equal to 3 times u squared. We have the following. F prime of x is equal to the derivative of h of u evaluated at g of x times the derivative of g of x, which is equal to 3 times x plus 2 over x minus 3 squared times minus 5 over x minus 3 squared, which is equal to negative 15 times x plus 2 squared all over x minus 3 to the 4th. And so notice this is an example of a generalized power rule. So in other words, if I want the derivative of a function to a power, that's going to be equal to r times f of x to the r minus 1 times the derivative of f of x. And so this is by application of the chain rule. So in other words, when we're looking at the power rule, instead of having just plain x here, we have f of x. So we're still applying the power rule where we bring the exponent out front and subtract 1 from the exponent, and we keep the inside the same, but we then have to multiply by the derivative of that inner function. So let's look at a couple of examples of how we could apply that generalized power rule. So here we have f of x is equal to x squared plus a to the m minus n power, where a is a constant, m greater than m are both positive integers. So again, we can use the generalized power rule. So here we're going to let the g of x, or that inner function, be equal to x squared plus a. And what we want is the derivative with respect to x of g of x to the m minus n. Well, we can apply that generalized power rule. Here our exponent is m to the n, or m minus n. So we're going to bring that out front. We're going to multiply that by the g of x, which in this case is x squared plus a, and then subtract 1 from the power. So I'm going to have m minus n minus 1. And then I just need to multiply then by the derivative of f of x. And here f of x is x squared plus a. So the derivative of that is 2x. And so we could write this then as 2x times m minus n times x squared plus a to the m minus n minus 1. And here is another example. So here we want to find the derivative of the 4th root of g of x. So again, notice we have, and we could write this as a power, we have g of x to the 1/4 power. So again, we can use the generalized power rule. And if we use the generalized power rule, we're going to have the derivative with respect to x of g of x to the 1/4. Well, using the generalized power rule, the 1/4 comes out front. We would multiply that by g of x, subtract 1 from the exponent, so we're going to have minus 3/4, and then we multiply that by the derivative of g of x. So that is going to conclude this set of notes. As always, if you have any questions over these, please let me know.